Hey everyone, and welcome back to Talk Tensors. We're diving deep today into a paper that could really change how we think about similarity between functions, at least in machine learning. It's called a similarity measure between functions with applications to statistical learning and optimization by Huang and Wang.
Yeah, it's a really interesting paper. At first glance, measuring how similar functions are, it might seem kind of niche, but it's a really fundamental problem that comes up all the time in machine learning. Think about it this way. A lot of machine learning algorithms, what they're really doing is trying to find the best solution, like the minimum of a certain function.
Right.
So this function kind of represents the problem we're trying to solve. And the landscape of that function, guides us toward the optimal solution.
Okay, so I'm picturing like a vast mountain range.
Yeah.
And our algorithm is trying to find the lowest valley.
Yeah. Exactly. Now imagine you've got a whole bunch of these landscapes, each one representing a slightly different problem, but maybe with some underlying similarities.
Oh, right.
So if we can accurately measure how close these functions are, it's almost like having a map that shows us how those valleys connect across different terrains.
I like that. Okay. So we could use that knowledge to navigate more efficiently.
Yeah.
Maybe even find shortcuts to better solutions.
Exactly.
So this paper is giving us a new tool to create that map, and it's called closeness, right?
Yeah, that's right. And it's not just about looking at the biggest difference between the functions at any given point. It's more nuanced than that. This measure really tries to capture the whole relationship between them, like how well do their valleys nest within each other, even if some of the peaks and valleys don't perfectly line up.
Okay, that's a really helpful image. Before we get into the specifics of closeness,
Yeah.
I think it would be useful to kind of understand the historical context a bit. Like, how do people try to tackle this problem of measuring function similarity in the past? How do we get to this point?
That's a great question. So early approaches were often focused on, simpler metrics, like just looking at the maximum difference between the function values. But that can be pretty limited, as we've been talking about. It doesn't really capture the whole picture of how those landscapes relate to each other.
Right, like two functions could be wildly different at one specific point, but overall, their values might be really similar.
Exactly. So over time, researchers started developing more sophisticated methods. One approach was to actually focus on the gradients of the functions, so like the slopes of those mountains, so to speak. If the slopes are similar, it kind of suggests that the functions are changing in a similar way.
Makes sense. So it's not just the absolute difference in height at any given point, but the direction of change that matters.
Exactly. Another approach was to look at something called the Bregman divergence, which basically measures the distance between the function values and their tangent lines. It captures how curved the functions are and how those curves relate to each other.
Okay, so we've got these different ways of capturing the relationship between functions, comparing their values, their slopes, their curvature. But it sounds like they each have their own limitations.
Yeah, they do. And that's kind of where the beauty of closeness comes in. It actually connects and unifies several of those existing measures. It provides a more flexible and powerful framework.
Okay, I'm even more intrigued now. So let's unpack this closeness a little bit. How exactly is it defined?
Yeah, so the paper, it lays it out formally in definition 2.1, but essentially, it's about capturing how well the suboptimality of one function predicts the suboptimality of the other.
Suboptimality. So how far off we are from that very best solution in each of those valleys.
Exactly. Let's say you have a point on one function's landscape. If the two functions are close, you can use that point and the closeness measure to estimate how far off you are from the optimal solution on that other function's landscape, within certain bounds, of course, defined by those Acme parameters.
Okay, so it's like having this guide that tells you, hey, if you're this far from the best solution here, you're probably within this range on the other landscape as well, even if the landscapes themselves look quite different.
Precisely. And to make it even more visual, the authors introduce this idea of sublevel sets. You can imagine slicing through those mountainous landscapes at different heights. And those slices, the areas where the function's value is below a certain threshold, those are the sublevel sets. And Lemma 2.1 in the paper, it shows that. If two functions are close, their sublevel sets are kind of contained within each other, with some scaling and shifting. determined by, OSIN.
Ah, I see. So it's not just about individual points, but about how whole regions of those landscapes relate to each other.
Yeah.
That's fascinating.
Yeah, and here's where things get even more interesting. They actually provide an example 2.1 in the paper, where you have two functions that look quite different at some points, but they're still considered close based on their overall relationship and this measure.
Okay, so before we jump into that example, I'm curious about something. We've talked about some of those earlier attempts to kind of capture function similarity, and now this new measure that seems to tie it all together. But where do you see this research going next? What are some of the future directions that you're most excited about?
Oh, that's a great question. Hmm. I think one of the most exciting frontiers is this whole idea of closeness-aware optimization, right?
Yeah.
Most optimization algorithms today are designed to kind of find that minimum of a single function, just in isolation. But what if we could build algorithms that actually use this knowledge of closeness, algorithms that could, strategically jump between functions that are close to each other?
Well, hold on. You're saying instead of our algorithm just trying to find the lowest valley in one mountain range, it could like leap to a whole nearby mountain range if it knows there might be an even lower valley over
Yeah,
there.
exactly. And the closeness, it would be like this guide telling the algorithm, hey, these functions are close, so their solutions might be related. You should go explore over there.
That's wild. But how would we even begin to design an algorithm that can do that? It sounds super complex.
It is complex, but that's what makes it such a cool research area. One promising direction, I think, is to look at meta-learning. Meta-learning is all about algorithms that learn how to learn. They can adapt to new tasks much faster than those kind of traditional algorithms.
Right. So instead of just learning from the data of a single task,
Yeah.
they're able to identify patterns in how the solutions to similar tasks are related.
Yeah, exactly. And if we can figure out how to incorporate this notion of closeness into meta-learning, we could potentially create these algorithms that learn not just from data, but from the relationships between different learning tasks. It's like building up a library of these solution strategies. And the algorithm can very quickly select the most relevant one based on, how close the new task is to the previous tasks that it solved.
That is a game changer. I'm already thinking about applications in like personalized medicine, where treatments could be tailored way more effectively, based on how similar a patient's condition is to others, or even robotics, where robots could learn to adapt to new environments and tasks much quicker.
Oh, for sure. The possibilities are pretty vast. But before we get too carried away, let's come back down to earth a little, back to the paper itself, and look at some of the more concrete applications that they actually explore. They dive into two main areas: empirical risk minimization, which is a cornerstone of statistical learning, and non-stationary online optimization, which deals with problems where that best solution is constantly changing over time.
All right. Let's start with empirical risk minimization. That's basically how we train machine learning models to make accurate predictions, right?
Exactly.
Like if we were building a system to recognize different kinds of fruit, we'd show it a bunch of pictures of apples, bananas, oranges, that kind of thing.
Right. You give the algorithm all those data points, your training data, and it tries to find the best function that fits that data and that function. That represents our model. And we want it to generalize well to new data it hasn't seen before.
So it's not just about memorizing the training data, but learning those underlying patterns so it can accurately predict, like, the type of fruit in a new image it encounters.
Yeah, exactly. Now here's where empirical risk minimization comes in. We usually only have access to a sample of the data, not the whole population.
Right.
So we try to minimize the error on our sample, hoping that it will kind of reflect the true error on that whole population.
Okay, so there's this inherent risk that our model might overfit to that training data
Yeah.
and not perform so well on new data.
Yeah, that's right. That's one of the key challenges in statistical learning. Traditionally, researchers have analyzed this problem by studying how close that empirical risk, so the error we measure on our sample, how close that is to the true population risk, which is like the error on all the possible data. And guess what? This is where closeness becomes really useful.
Okay, yeah. It seems like the perfect tool for this kind of analysis. So how do the authors actually use it?
Well, they show that if that empirical risk and the population risk are close, then the solution that we get by minimizing that empirical risk is also going to be a pretty good approximation for the true population risk minimizer. It basically gives us a way to actually quantify how well our model is learning from that limited data that we have and how confident we can be that it's going to perform well. on new data.
So it's like a measure of how reliable our training process is. Like how well does our sample truly represent that whole population?
Exactly. And they even go a step further and explore how this framework can be applied to situations where the population risk function is strongly convex.
Strongly convex. Remind me about that again.
Yeah.
The bowl analogy, right?
Yeah, you got it. Imagine you've got a bowl, right? With a single deep point at the bottom. That's a strongly convex function. There's only one clear best solution. And in these cases, our model can actually learn much more efficiently. And the authors show how that part of the closeness plays a crucial role in understanding that efficiency.
Because it captures how those suboptimality gaps between the functions relate to each other.
Right.
It's not just about the absolute difference in their values.
Exactly. It's that more subtle relationship that gives us a more precise understanding of how well our model's actually learning. And what's interesting is this ties back to some of those existing techniques in statistical learning theory, like the peeling technique, which also uses this idea of relating suboptimality gaps to get, tighter bounds on the error.
And that's really neat. It seems like closeness is providing this like unifying framework for understanding so many different aspects of empirical risk minimization. But what about that other application you mentioned? Non-stationary online optimization.
Yes. That's where things get really interesting and very relevant to the world we're living in today.
All right, lay it on me. What is non-stationary online optimization? And why should I care?
Okay, so imagine, right, you're trying to optimize something, but the environment is constantly changing. That's basically what non-stationary online optimization is all about.
Okay.
Think of algorithms that have to adapt to changing user preferences on a platform like Netflix or a self-driving car, trying to navigate through unpredictable traffic. That best solution, it's always shifting. And the algorithms, they've got to keep up.
Yeah, I'm starting to see how dynamic this is and how challenging it must be. So how does this new measure closeness, how does it help us deal with that?
So the key here is that by analyzing the closeness between functions at those different points in time, we can actually get some really valuable information about how much that problem is actually changing.
So if those functions are, really close together,
Yeah.
it suggests that things are pretty stable. But if they start to drift apart, that means we're dealing with some big shifts in the landscape.
Yeah, exactly. It gives us a way to actually quantify the degree of non-stationarity, which can then be used to design more robust and adaptive algorithms. And what's really cool is that the authors, they show how closeness connects to all these different ways of measuring variations in these dynamic environments, like looking at the difference between, the functions themselves, their gradients, or even the locations of their optimal solutions.
So it's like this new measure is giving us this unified way of understanding and analyzing these different types of non-stationarity. We're not just limited to one perspective anymore.
Yeah, exactly. And it opens up a whole world of possibilities for designing these algorithms that can really handle these real world scenarios where things are constantly changing.
This has been, wow, just an amazing deep dive. I'm still kind of wrapping my head around the implications of, this whole new way of measuring function similarity and all the potential applications from statistical learning to optimization in these crazy dynamic environments. Like we've got this whole new toolbox for machine learning.
I know, it's really exciting stuff. And it really highlights how, even these seemingly abstract mathematical ideas, they can have a huge impact on solving these real world problems.
For sure. So if our listeners want to dive even deeper into, all the nitty gritty details of closeness and the math behind it all, where can they find the paper?
We'll be sure to include a link to the full paper in the show notes, so check that out. And hey, maybe this will inspire some of you out there to develop the next generation of closeness-aware algorithms.
That's it for our exploration of a similarity measure between functions with applications to statistical learning and optimization. By Cheng-Pia Huang and Kai-Sheng Wang. Until next time, keep those learning algorithms humming and those functions close.